Hello, in this video we're going to look at the dynamics of the coronavirus or COVID-19 pandemic. I've obtained some of the statistics that we will need from the Worldometer's website at this web address. So if you want to look into it in more depth yourselves, then that would be one of the places where you could go to look at more in-depth statistics. Now, for this mathematical model, I've specified some of these statistics, starting off with the number of infectives T months after the pandemic outbreak. So this is equal to X of T, meaning the number of infectives at time T. And we just put that equal to X for simplicity. That will appear in our equations later on. Now, I've had to make an assumption to begin with that there was only one infective at time T equals 0. Now, what do I mean by time T equals 0? Well, I've taken that to be about 4 months ago at or close to the beginning of December 2019. So I've assumed that close to the beginning of December 2019, there was only one infective. I know there might have been a couple or so more who then spread it to the wider public, which then had a kind of a cascade knock-on effect for the rest of the world. But we're assuming here it's just one for simplicity. Another piece of information we need is how many infectives are there now? Well, we're now 4 months on, roughly, and according to the Worldometer's website, there are almost 500,000 infectives. I think it's a little bit less than that at the moment, but by the end of March 2020, it will the number of infectives will be getting on for 500,000 across the world. Of course, we're maintaining social distancing, and a third of the population is currently in lockdown, so the spread of the virus will probably be slower than it would normally be. This is what they mean by flattening out the curve, so that hopefully X months down the line, it will burn out quicker than it would normally. I've specified that the carrying capacity is N, capital N. This is equal to the total world population of 7.5 billion people, or 7.5 times 10 to the power 9 people. Now, in this model, we assume, we make an assumption that we can ignore deaths. And this is because one of the assumptions is that the number of deaths compared to the number of those who have recovered and compared to the whole population is relatively low. I think about 80% of the population recover from coronavirus or COVID-19. So that leaves about 20% possibly who don't, but we assume that that is relatively negligible compared to 80%, which is still a very high value. Now, I've asked the question once again, how long will it take COVID-19 to completely run its course and burn out? Or I should say, really, how long will it likely be for COVID-19 to completely run its course and burn out? Because we don't know for sure about that. It partly depends on the social distancing and other factors. Now, as I specified here, the COVID-19 pandemic could be modelled according to the logistic equation here. what you will notice is that this is an ordinary differential equation, and what this says is that the rate at which people get infected, which is this dx by dt, the rate at which the number of infectives increases is proportional to the number of infectives at any time t multiplied by, in brackets, 1 minus x, being the number of infectives at any time t, divided by n, close brackets. Of course, where you've got a proportionality sign, you want to insert an equal sign and a constant of proportionality. So this equation now becomes dx by dt is equal to kx times, in brackets, 1 minus x over n, close brackets. And again, x is the number of infectives at any time t months after the outbreak of the disease. Now, how do we solve this equation? How do we get to some kind of final solution where we can predict not only how many people will have recovered from the disease, for example, X months down the line, but how many months that will take before the virus has burnt out and we can revert to some kind of normality in quotation marks, of course, because there may be changes after this. Now, the approach that we take to solve equation 1 here is to separate the variables. So I'm going to make a start with that. So we've got dx by dt here, and we want to divide both sides by x. I can't actually highlight all of that. Oh yes, I can. X, we want to divide both sides by x times 1 minus x over n, and we want to multiply both sides by dt. So if we do that, we've got dx, I'll try and make that a little bit neater, because I'm still getting used to my electronic pen and everything. So dx divided by x times 1 minus x over n, and we just leave it like that, and that's equal to k dt. And of course, when we separate out the variables, we want integral signs. We take k as a positive constant, although it may come out to be negative later on. So let me just write that in a little bit more neatly. Now, to actually solve this equation, we need to express the left-hand side in terms of partial fractions. Now, I'm not going to go through how to work that out. I'm just going to specify what 1 over, let me just delete that. I'm just going to specify what 1 over x times 1 minus x over n actually is in terms of partial fractions, and that comes out to be 1 over x plus 1 over, let me just make that a little bit straighter, n minus x. So that's what that is equal to. So we can express the left hand side as the integral of well, it's going to be dx over x plus the integral of dx over, try and keep my pen straight, dx over n minus x is equal to k times the integral of dt. Now, I'm going to change the variable x to a dummy variable y because I want to insert limits to try and maybe make the analysis a little simpler. So we'll put these integral signs in here. Now, at time t equals 0, we've got an initial number of infectives. So this is the number of infectives at time t equals 0, and of course you have to put that there as well. And that goes up to the number of infectives at any time t after the outbreak. And so we have t there. So at time t, this is the number of infectives. And of course, because we've got t at small t as a limit, we can't have it as a variable as well. So we just substitute d tau or tau in for the differential element. Now this becomes dy over y, and this becomes dy over n minus y. So we can go ahead and solve that equation. Now, I'm just going to leave the page as it is there so that it's easy for me to see what I've written on that last line above. But basically, if you take logarithms, you get the log, if you integrate the left-hand side of that equation, you get logarithms. So I have to think carefully about what I'm saying, and that should be a plus there. So we've got log of y plus the log of n minus y equal to k tau. Now, I haven't finished with that line. I'm just going to erase that and put it a little bit closer to here. Now, we've got to put the limits in. So that goes from x0, let me make that look a bit more like an x, x0 to x. This also has the same limits, x0 to x, and that goes from t equals 0 to t. In fact, we could just say 0 there. I do apologise for my handwriting because I'm not very good at actually writing on these pads, but there are other benefits, which is why I do it. So please bear with me. So we've got the logarithm of y. If we substitute in the x for y, we get the log of x minus the log of x0, put modulus signs in for now, plus the log of n minus x minus the log of n minus x0, and that's equal to kt. Because if you substitute 0 in for t, you just get 0, and of course if you substitute the t in, you just get the kt. Now this can be simplified a little, and I'm going to do it in stages so that we get it right. So we've got the log of, just let me write that a little more neatly. I'll try and get my pen straight. So we've got the log of x over x naught, x sub 0. Put the modulus signs in, plus the log of n minus x. In fact, actually, these modulus signs should come right down there. Let me see if I can put those in without having to delete everything again. Right, okay, n minus x over n minus x naught. and that's equal to KT. Again, I hope that's reasonably clear. I think what I'll do is I'll just erase these modular signs because it does look very untidy and not very neat. Let me just click on that black pen again. So we've got X. Now let's try and draw down. There we are. That is a little bit better, but not brilliant. Now then, in actual fact, I've actually made a mistake in the integration because when you integrate this here, you actually get a minus sign here. So many apologies for that. So you get a minus sign there, and that becomes a plus. So we could actually have that in brackets, really. So you could put that into brackets like that, and then multiply out by the minus sign to get a plus there. So that's me not being careful again. So we get this, and if you simplify that further, you can write down the log of x over x naught. And by the laws of logarithms, you get, oops, making a mistake there, divided by n minus x over n minus x naught, right? And that's equal to kt. So if you simplify that a little bit further, you get logarithm of x times n minus x0, x sub 0, over x0, let's put that in, times n minus x, and modular sign equals kt. Right, okay, so let me put that bracket in there. Forgotten a bracket. Now, we've got a logarithm on the left hand side. How do you get rid of that? Well, you should remember that to get rid of a logarithm, you just take the exponential. So you're left with, so we'll just say taking exponentials of both sides, we get, well, you just get x times n minus x sub 0 here. Oh dear, I cannot draw straight lines, can I? So, right, there we are. I need to probably take my time and be more careful. N minus x there, and that's equal to e to the kt. Now, we're certainly getting somewhere, because we can now multiply both sides by, and I'll write this down, multiply both sides by x naught n minus x to get, I'm going to write it over here because I think the working starts to become more a little messier, you know, and so it's x times n minus x 0 equal to x naught n minus x e to the k t. And we've got to multiply that right hand side out. So therefore, let's get this pen in my hand correctly. There we are. So we've got x n minus x sub 0 equals x sub 0 n. Let me just, that's not great, is it? X sub 0 n e to the k t minus x naught x e to the k t. Okie doke. Right. So what we do is we want to collect all the x's together, and so what we do is we bring all of this to the left hand side. So we've got x on the left hand side already times n minus x naught close bracket plus x naught x e to the k t equal to x naught n e to the k t, right? Now what we do is we don't need to multiply this out by what's in the bracket. We can just leave that as it is and factor out the x from both terms. So we factor out this and we factor out that. So we get, and I'll write this in blue, x times, in brackets, n minus x naught plus x naught e to the k t. And that's equal to x naught n e to the k t, right? So what we do now is divide both sides. So we'll write this down, divide both sides. I want to make that look a little more neat. Sides, divide both sides by n minus x naught plus x naught e to the k t. So we'll just put that in brackets to get and we'll just scroll up a little bit. Right, so we get x equals x naught n e to the k t over n minus x naught, make that look more like a minus sign, plus x naught, I wasn't watching, x naught e to the k t. Now you could leave it like that, but it's a bit messy as it stands, because we only, if we can, we only want one exponential term in this whole equation or expression. We don't want two. It just makes the working harder when you try to work everything out. So if we divide both sides, so well, I'll write this in blue. Divide both sides by x naught e to the k t to get, let me just scroll up a little bit, try and keep that just showing. Right, okay. So we'll highlight this in red again. So we get x equals n in the numerator divided by, well, we get, let me just see, what have I got? N over x naught, because you divide each of these terms here by x naught e to the kt. So you get n over x naught minus 1 want to make that look less slanted, n over x naught minus 1, and that's all times e to the kt plus 1. So that's what you should get if you divide the numerator and the denominator by x naught e to the kt. You should get that. And that is the final form of our equation. Now, I call that, we'll call that, I always highlight the equation numbers in red. So I'll write down that that's equation 2. Now, what do we need to do now? Well, we are given that x naught equals 1, and n equals 7.5 times 10 to the 9. So we have if we substitute those values in, let me just scroll up a little bit. So we have x equals 7.5 times 10 to the 9 over 1 plus, I'm just changing the denominator around to put the exponential part coming last. So 7, and I'm actually going to write all of this out because I think it's kind of important to be precise. I know it's a very long number, but I think it's important to be as precise as possible in this case. So kt, right, now we can go on to the next part. Right, but we have x of 4 equals 500 infectives. This means that when t equals 4 months, x is equal to 500,000 infectives, or people who are infected with the virus. That's COVID-19. Right, okay, so what do we do? Well, we substitute in 500,000 here, and we substitute 4 in for t. And what we get is, right, so what we get is 500,000. Why does my writing run into other words? So there we are. So we've got 500,000 equals 7.5 times 10 to the 9 over 1 plus 7 point, excuse me, we're writing it out as a whole number, 99999 e to the 4k, e to the 4k. Let's just draw that line up there. Whoops, it really it's very difficult to draw straight lines on these writing pads. Okay, so now we can work out k. We can now determine a value for k. So what we do is we multiply. So multiply both sides of the equation by I'll put it in brackets, 1 plus 7,499 999 e to the 4k to get let's scroll down. Well, we get 500,000 times 1 plus 7 499 999 e to the 4k equals 7.5 times 10 to the 9, 7.5 billion. Now, if you multiply this out, you get 500,000 plus 3.75 times 10 to the 15 e to the 4k, and that's still equal to 7.5 times 10 to the power 9. Then subtract 500,000 here. Subtract 500,000 from both sides. It should be fairly elementary. So we get 3.75 times 10 to the 15 e to the 4k equals 7.5. I should have just written down the number, but anyway, minus 500, 1, 2, 3, 500,000, and let's just, that's it, right, okay. So this comes out to be equal to 3.75, should put therefore, 3.75 times 10 to 15 e to the 4k equals, what have I got here? 7 point, whoops, just eliminate that, 7.4995 times 10 to the 9. Dividing both sides by 3.75, So dividing both sides by 3.75 times 10 to the 15, we get e to the 4k is equal to, I'm actually going to write this out with quite a few decimal places. 8, 6, 6, 6. You would write it to say 3 significant figures or something like that. But the thing is, this is 10 to the minus 6. So if you take, if you remember, to get rid of an exponential, you take logarithms. So you get 4k is equal to the log of 1.999866667 times 10 to the minus 6. Now this is a really tiny fraction on the right hand side, the part that's in the argument here, and that actually comes out to be minus 13, I think, minus 13.122 43005. But if you divide them by both sides by 4, you get k equals minus 3.28. We call it 2806 to 5 significant figures. Right? So if we go back to equation, and I'll actually call this equation 3. We get, so if we substitute k, our value for k, back into equation 3, just a moment, I want to show you that in a few minutes. Let's just scroll up. Right, so we get x equals 7.9 times 10 to the 9, all divided by 1 plus, I'm actually going to write this out, but you could probably approximate it to 7.9 times 10 to the 9. But I don't really like doing that. You can't always do that with these things. 49999. Whoops, they're looking less like 9s, aren't they? Right, let's just 99999. I think that was a case of 9 fatigue. And we'll just write it, just extend that a bit longer. Now let me just erase that little bit of a, I'm actually going to write this in as, oops, just let me go back. Let's click on the red pen, EXP minus 3.2806t. And that is the function. Of course, I was actually going to write it as, just write it in blue, in a form that you might be more familiar with in terms of that exponential. So it's 7.9 times 10 to the 9 excuse me, over, there we are, 1 plus 7, 4, 9, 9, 9, 9, 9, 9, 9, 9, e to the minus 3.2806 t. And that is the general solution. We'll call that equation 4. Now, if we plot equation 4, and you got a sneak preview of the graph, if we plot equation 4, we get the following sigmoid because it's S-shaped graph. My writing is so bad, isn't it? Never mind, I hope you can see that. So if we plot equation 4, we get the following sigmoid or S-shaped graph, or curve, more correctly. And if I just press on delete, we can get this up to the top, and that is what the graph looks like. Now, this at time t equals 0, 0 months. So back at the beginning of December, there was only one infective here. As time has progressed, we've got to 4 months, and there are still very few people who have been infected, but it's spreading fast. Now, as time goes on, in another 2 months, the curve will be about here. So we'll be at 6 months. So January, February, March, April, May, June. So by about June, more and more people will be becoming infected with COVID-19. And then all of a sudden it will shoot up over the following 2 months to August, round about the 1st of August, when it will begin to plateau out. So by the time we get to 8 months, which is 8 months from the beginning of last December, that will be all of December, January, February, March, April, May, June, July. So by the end of July, which is here, the beginning of August, the pandemic should, I predict, start to burn out, and we should be able to return to some level of normality, whatever normality actually means. So basically, again, just to recap, this is time t equals 0, beginning of December. This would be the beginning of February. This would be where we are now, nearly the beginning of April. So that's nearly 4 months since the outbreak started. And in another 2 months, by the beginning of July, end of June, beginning of July, the virus will start to accelerate and then kind of shoot up over the following 2 months towards let me see, July, August, to about the 1st of August, just into August. The disease should start to plateau out. That is where everybody has had the virus, and in this case, these are recovereds or people who haven't had it, but particularly those who have recovered. It doesn't take into consideration an explicit death rate. But that's basically what we're looking at. So we're at the end of, nearly at the end of March now. So in about another 4 months, I think it is, March, April, May, June, July, another 4 months, we should hopefully be over the coronavirus, but don't quote me on that. It could be longer, it might be shorter, but that's what my mathematical model suggests. So this is only one model. So I'm not saying this is written in tablets of stone whatsoever, but that will give you some idea of what's happening in this particular case, and hopefully it'll give you an idea of how to model diseases in the future, because it's a similar sort of process. But of course, it does get a lot more complicated, and sometimes you might have about 3 or 4 different equations that you've got to solve simultaneously, because they do consider more explicitly susceptibles, infectives, and deaths, and things like that, and recovereds. So that does get a lot more complicated, but this is just a relatively simple model that seems to suggest that this is the nature of the current coronavirus or COVID-19 pandemic. So I hope that's been informative for you, and that you've got something out of it. And it just remains for me to say, please do come back and look at my other videos, and I hope to be uploading more in the future. So I'll bid you farewell for now, and see you soon. So bye for now.